Monday. I am going out of town tomorrow morning early. I'll be back on Friday afternoon. So if you need to see me or talk to me, then by all means email me. I'll be available to you. Even if we have to do it over the phone or over Zoom or whatever, I can do that. I have a tablet at home. I can do that. Or if we need to meet, I can probably do that too. But it might be later in the afternoon before I can do that on Friday. Okay. Or if we need to do it on Saturday, that's fine too. Yeah, Ben? Huh? Right. No class on Friday. It's already listed as an online class, but since we're this close to our exam, I'm not going to start chapter 8. We're just going to have it be y'all prep for the exam. Okay? Also on Monday, just beware, I'm out on Monday as well. I'm going to HL. I'm going to the dry house. Oh, let's wait over. Well, no. You got HL? No. I'll go to the dry house. Okay, anyway, so I'll be at HL all day, so I'm not going to be here for the exam. I think I have my wife proctoring this class, so just beware that she's the one that will be here to help you. If you have a question about the exam, she can answer those questions most likely. Of course, she can answer the questions. But if you don't get a satisfactory answer or she doesn't know the answer, you can just write your question on the exam, and then email me when you get out, and then I'll go look at your question and I'll say, well, if I had answered this, would have just changed your answer, and I'll address that with the whole class. Okay, so if you have a question, just write on your exam and email me afterwards. I don't think it's going to happen. I'm working the exam a couple times. I didn't see any errors. But, I'm not perfect. Am I?
Let's see how you promise with it.
I will. Yeah. See what I'm doing, man. All right? Monday. Yeah. So it's Monday. Oh, I didn't get you on the list. Let me, All right. I want to work through this number 4 first, because we worked through numbers 1, 2, and 3. This is the fall 22 exam. Numbers 1, 2, and 3 are going to be on there. Very similar. I've largely just changed the numbers. And that'll be true for this number 4 as well. We work problems like this, but we haven't worked this specific problem. So let's look at it. First, we're just going to write down the things that we know. I know that I have this around the world with a yo-yo. It's spinning in a vertical circle like this. It's a lot like the Ferris wheel, by the way, that problem that we did. As it spins in this vertical circle, it's spinning at a rate of 6 radians per second. That would be the angular velocity. It has a mass of 0.2 kilograms. And I tell you that the radius of the path is 0.5 meters. Actually, I intended 2 sig figs. I'm going to write 0.50 meters. So that's the radius of the path. The first thing that I want to know is just what is the centripetal acceleration? I know that AC is equal to v squared over r. That's not on your equation sheet explicitly. This is what you have on your equation sheet, that FC is equal to mv squared over r. However, also recognize that FC is equal to m times AC. So this term right here, that is your centripetal acceleration. Okay? So AC is v squared over r. Here you can do one of two things. You can calculate v. You can say v is equal to omega r, and then calculate v. Or you could substitute that omega r in for v, and you get an alternate expression for the centripetal acceleration, which is omega squared r. I'm going to do the latter, because we already know omega, and so we can use this expression. It just makes it a little easier. So that's going to be 6 squared. That is omega times r, which is 0.5 meters. So that's equal to 18 meters per second squared. That's the centripetal acceleration. That's part A. That's all you have to do for that one. For part B, it's a little more complicated. I really recommend that you draw a picture. It'll help you to think through the signs, and you'll actually have one of 3 variations for this part. Otherwise, the problem is going to be really similar. I ask, what is the centripetal acceleration and what is the tension? But I might ask at the top, the bottom, or the side. So let's look at all those. I'll do the top first. So imagine I have this yo-yo. It's following a circular path of a radius of 0.5 meters. Imagine at the top, the yo-yo is here. There are 2 forces now acting on this yo-yo. There's the tension in the string, Ft, and then there's also the weight of the object. And then also recognize that the acceleration is in the downward direction. The centripetal acceleration is always towards the center of the circle. So the acceleration here is downward. It's in the negative direction. Now, I can apply Newton's second law. The sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. That's just Newton's second law. The sum of the forces is negative Ft minus Fw is equal to m times the centripetal acceleration, but recognize that that centripetal acceleration is negative because it's towards the center of the circle and in the downward direction. Now also recognize that I can multiply both sides of this equation by -1, and it makes all those positive. So then if I want to find Ft, Ft is equal to mac minus Fw. That's equal to the mass, which was 0.2, times the centripetal acceleration, which I've already found to be 18, minus the weight. It has a mass of 0.2 kilograms, so it has a weight of 2 newtons. That's going to be equal to 1.6 newtons. 3.6 minus 2 is 1.6 newtons. That's at the top of the trajectory, at the top of the path. At the bottom of the path, is the tension going to be bigger or smaller? So have you ever done a yo-yo, around the world yo-yo? Yeah. At the top, what happens to the tension? Does it go tighter or does it go more slack? It goes more slack. If you ever watch them, sometimes they'll even fall a little bit. If they're not going quite fast enough, they'll fall a little bit. If you're going fast enough, you should have it taut. But the tension at the top will be less than the tension at the bottom. So let's imagine then, what if I wanted to find the tension at the bottom? Same problem. I have a tension in this direction. My weight, though, is in that direction. And notice my centripetal acceleration is towards the center of the circle, so it's in that direction. Same thing that you do here. You say Ft minus Fw is equal to mac, and now my AC is positive because it's upwards. If I want to know the tension is equal to Fw plus mac, which is going to be, in this case, 3.2 plus 3.6, which is 5.6 newtons. So here it was at the top. This is at the bottom. The third thing that you'll need to do, or the third variation that I could give you on this, would be at the side. The side is actually a bit easier because at the side, notice the forces. I have the weight, which is down, and the tension, which is towards the middle, towards the center. Also, the centripetal acceleration is towards the center. Since I'm looking for the tension, I would say the sum of the forces in the x direction are equal to Ft, and that's equal to mac. So that means that the tension is equal to 0.2 kilograms, that's the mass, times the centripetal acceleration, which is 18, which would be 3.6 newtons. So 3 variations on that, but the process is all the same. Don't try to memorize the equations. Instead, if you're memorizing anything, memorize the process. That I draw my vectors. The tension is always going to be towards the center of the circle because it's a string, right? So the string is attached here. So that tension will always be towards the center of the circle. And the centripetal acceleration will always be towards the center of the circle. That's what centripetal means. Center seeking. It's always towards the center. The weight will always be down. And so it depends on where you are on this circle, the top, the bottom, or the side, as to what is going to be the arrangement of these vectors. And then you say the sum of the forces equals ma, that's Newton's second law, and solve for tension. But the difficult part of that problem are the signs. Getting the signs correct. Definitely the most difficult part. Practice it, okay? It'll be on your exam. Problem number 4. Make sure you practice it over and over So that when you come into the exam, that it's just, like, you don't have to think about it. That's really what I want in those 3 responses. You don't have to think about them. You just come in and you do them. You've done them so many times that you don't even really have to think about it. Okay? All right. Are there other particular questions that you want me to work? If not, I'll just sort of scroll through and show, we'll highlight some things. Particular questions? No? All right. So you're gonna, the test is more heavy towards chapter 5. Right? There are 2 free response questions, so that's 4 questions. And then I think there were 8 or so multiple choice questions. So that's 8 plus 4, that's 12. Almost half of the exam is from chapter 5. And then chapter 6 and 7 make up the other parts. Chapters 6 and 7 are pretty equal in their distribution. There's just more stuff in chapter 5. You have this free response question with the work energy problem for the inclined plane that requires you to think about the frictional force. But instead, let's go to the back of your book since y'all have that paper in front of you. So let's go to the Fall 21 exam. You'll find that these exams are very similar. So practicing them will help. So let's look at the Fall 21 exam, number 3. This is a work energy problem. I have a block of mass 10 kilograms with a certain speed. It travels across a rough surface, and after traveling a certain distance, it now has a lower speed. So let's think about what's happening here. Draw a picture. I find that always helps me just to start by drawing a picture and then writing the things that I know and the things that I want to know. I will also say that there are 2 equations that you'll need to know that are not on your equation sheet. That includes these 2. The frictional force is mu times the normal force. And when I have an object on a horizontal surface, the weight and the normal force are equal to one another. Of course, we know that's not always true because if I have other forces that are pushing down on it, then the normal force can be bigger or smaller than the weight. But for the sake that we're doing, the normal force will always be equal to the weight. I'm not going to have you dealing with any components of vectors. So the normal force here is equal to the weight. And the weight, of course, is equal to m times g. So anyway, here I have a block of 10 kilograms. It has a speed of 4 meters per second. It's traveling in this direction. It travels through a certain distance, we'll call that d, and at the end, it has a speed of 2 meters per second. And I want to know what is the coefficient of kinetic friction that is acted over this surface right here in order to make this block slow down. The block starts with a certain amount of kinetic energy. The friction does work on it, taking away that work, and then it's left then with a final amount of kinetic energy, a smaller amount of kinetic energy. So I can say 1/2 of m times v squared, that's v initial, minus the work done by friction, that's going to be the frictional force times the distance, equals to 1/2 m v final squared. I can put in numbers here. I'm looking now for the frictional force. So the frictional force would be equal to 1/2 m vi squared minus 1/2 m vf squared divided by d. You could actually go a step further and cancel out that mass, but we're not going to worry about that here. So that's 1/2 of the mass, which is 10. That's 5 times vi squared, which is 4 squared, 5 times 4 squared, minus 5 times 2 squared, divided by the distance, which is 2 meters. And that gives me a frictional force of, what's 5 times 16? 80. 60 divided by 2, 30. You did that right? Yeah. Okay. So my frictional force is equal to 30, but really I'm asking for the coefficient of kinetic friction. So I say F, which is equal to 30, is equal to mu times the normal force. The normal force is equal to 100 because the mass is 10. So mu is equal to 30 divided by 100, or 0.3. You're going to definitely see 2 or 3 work energy problems. The one in the free response with the inclined plane, one similar to this as well, and there might be one other as well, okay, that are something similar to this. Of course, you're going to see like the roller coaster problem, both conceptual and calculations. Are there any particular problems, just sort of as I scroll through this? Going to see spring energy problems, total work done on the block here. For this block, it would be 8 cosine 60 times 3 minus 1 times 3. You have to consider both forces and the work that's being done. We can work through that if y'all like. Just let me know, holler out. Hooke's law, you're going to see that. You're going to see at least one question asking the basic SI units. That would be for either work or energy. Those would be the same, actually, work and energy, or for momentum. It's gravitational potential energy. Any of these y'all want to work through? Just holler a number if you want me to work through it, I can. All right. I've told y'all this, for the free response, you're going to have a perfectly inelastic collision. This is a perfectly inelastic collision. In fact, this looks a lot like your free response question. The numbers are different, of course, and maybe the directions and stuff. But let's work through it just for practice. This is number 12 on the exam in the back of your book, right? This is in the back of your book, right? Yes, okay. So the signs are really important here, so make sure that you get the signs correct as you're writing down the values. In fact, you might want to just go through before you start and label those velocities with signs as either positive or negative. I would start with the conservation of momentum. PI is equal to PF. That would be 2 times positive 3, the mass times the velocity, plus 4 times V2I will be equal to, well, these two combined are 6 kilograms, so 6 times negative 6. And that's so it's going to be 10.5 or 11 meters per second. It's actually going to be negative 11 meters per second, but I'm just asking for the speed here, which is the magnitude. So none of them have positives or negatives. Okay, but it is to the left, that speed or that velocity. All right. Well, let's work number 13 as well. This is a collision problem, and you'll have one similar to it. We did one like this in the concept test question. I think we did one similar in the notes. Here I have a railroad car that has a mass of 2,000 kilograms and is traveling with a speed of 4 meters per second. It runs into a stationary car with an identical mass, so also 2,000 kilograms, but it has no speed, it's stationary. And then they connect, the railroad cars, right? So they connect to one another, and they have a total mass of 4,000 kilograms. And I want to know what is the speed of the two cars. I actually know it's going to be going off in this direction, right? Because the initial momentum up here was to the right, so this one will also be to the right. So I'd say 2,000 times 4 plus 2,000 times 0 is equal to 4,000 times VF, which is going to be 2 meters per second. The mass doubles, so the speed is going to halve. All right. Otherwise, in chapter 6, you'll see impulse problems. Those are those problems where either you're just finding the impulse, which is our delta P, which is M delta V. In this case, that would be 2 times 3 minus negative 4, which is going to be 14 meters per second. Notice what happened there with the signs, that when I have something that changes direction, going to the left to going to the right, then I'm going to actually be taking the sum of the two velocities. We saw that in class. Anytime you have a rebounding object, like something that starts in one direction and goes in the other direction, because of the way the signs work and the change in velocity, I'm going to actually have the sum of the two numbers instead of the difference of the two numbers. However, if I have an object that's just changing speed, say slowing down or speeding up, that's not true. If it continues on in the same direction, then your change in velocity will just be the difference in the two numbers, which is, yeah, it's not like this, but we can do number 5. So you could have an impulse problem. I'm pretty sure you do actually, where you just have to calculate the impulse. Also, to find the force, or in this case, we're looking for the speed, the final speed. But I'm always going to start with this. So anytime you see force, think delta P over delta T. That's what I'm looking at. That's going to be 20 newtons equals M times my change in velocity over T. My mass, though, here is 10 kilograms. And my delta T is equal to 4 seconds. So that's 80. So delta V is equal to 80 divided by 10, or 8 meters per second. Since it started at rest, then its final speed is going to be, just 8 minus 0, or 8 meters per second. But if it wasn't starting at rest, you'd have to find the difference in those two numbers. All right. This is actually a lot in chapter 3. There's also chapter... Sorry, let's go to exam 4. So any other questions for chapters 5 or 6? I want to look at rotation now. Chapters 5 or 6? Y'all feeling okay about this exam? I know it's still early, that y'all haven't really started deep into your preparation. I'm sorry for that this is coming so early. But again, I will be available to you on Friday afternoon, probably later in the afternoon. So if you want to meet, just let me know. It'll just be, me and whoever else wants to meet. If y'all want to, if you need extra help on Friday afternoon, I'm available. Okay? All right. Let's go to your exam 4 in the back of your book. That year, we had quite a few questions from chapter 7 in exam 4. So y'all have 21, right? You can follow 21. Yeah. So from chapter 7, you're going to have some problems where you're finding using your kinematics equations. That's the theta equals omega naught t plus 1/2 alpha t squared, that whole jazz, all that jazz. And then you're also, and the omega equals omega naught plus alpha t. But then you're also going to have problems where you're finding the centripetal force. Kind of like with the yo-yo problem, but simpler. We'll see. I'll show you some examples. You're also going to have to convert between revolutions and radians and degrees in order to find the velocity of an object at a rotational velocity or a rotational displacement. Know your unit circle. Right, number 2 here. Make sure that you know how to change from degrees to radians and revolutions. Let's see, you're not going to see a number 3 because that's in your free response. But you could see one like number 4, where I'm just asking what is the centripetal force? That is, what force is causing this object to move in this circular path? I think we've done this problem actually. F is equal to mv squared over r. That's my centripetal force. You have to do some conversions here. Notice that here omega is 2 revolutions per second, but you must be in radians per second when you're doing this. So that would be 2 times 2 pi or 4 pi, or about 12 radians per second. I just multiplied this. 1 revolution is 2 pi radians. So that's my omega. If you want to find V, you could say V is equal to omega R. That's 12 times R, which is 1.5, which is 18 meters per second squared. So I have the mass, which is 5 kilograms, times 18 squared, divided by the radius, which is 1.5 meters. It's the length of the cord in his arms. So that is I get 1080. I was rounding. I rounded the omega, so it must be C is the right answer. 1,200 newtons. That's a big force. That's why a hammer throw is so difficult. If you're slinging a, ever done the hammer throw? You might. No, me either. But it's a big force. Okay. You're gonna have to do kinematics questions like number 5. Just like we did in chapter 2, the easiest way is just first is begin to write down the things that you know. Make sure you know what omega, theta, and alpha all mean. If it starts at rest, that means omega naught is equal to 0. That's the initial angular velocity. I cause it to accelerate at 2 revolutions per second squared. And I want to know how long does it take for it to go through 2 revolutions. On these kinematics problems, you don't need to worry about changing the units. They'll all cancel out in the end as long as they're consistent within, which for your exam, they will be consistent within the problem. It's when you're calculating centripetal forces or when you're doing these conversions, V is equal to omega R, A is equal to alpha R. In those cases, you have to convert to radians. Anytime you have a question about it, just convert to radians. You're never going to go wrong converting to radians, but you might have to convert back in order to get the right answers. So you have to check the units in the answers. All right, so here I want to know how long does it take. Let's write down my equations. Omega is equal to omega naught plus alpha t. These are on your equation sheet. Omega naught is 0, so that all these terms go away. And then I know alpha, theta. I know alpha and theta. I know this and this. I'm looking for time, so I can find it from there. So I say 2 revolutions is equal to 1/2 of 2 revolutions per second squared times t squared. So t is equal to the square root of 2, which is 1.4. All right. You'll see 1 or 2 questions like that for kinematics, rotational kinematics. There's another similar one, like for number 6. You'll see some of these questions. We did some of these in class where an object is rotating through a certain time or angle, and I ask you what happens if you change that time. Remember that theta is proportional to t squared. Omega is proportional to t. So for example, if I double t, I quadruple theta. But if I double t here, I just double omega. Look at those equations. They'll remind you of that relationship, but you will see at least one question like that. You'll also see questions like number 7. I think there was a similar question with the Earth that we did last time, where something that you know how long it takes to rotate, like the Earth rotates in 24 hours, the second hand of a clock rotates in, 1 minute, 60 seconds. So you should be able to find the angular velocity. In this case, that angular velocity would just be theta divided by t, which is 1 revolution. I know 1 revolution because, look, I looked at the units, and they were all in revolutions, divided by 60, and 1 divided by 60 must be 0.017. Yeah, that's right. You'll see some like 8 and 9. Stop at 10 here, so not like 11. Yeah, I'll look back through that exam. Are there any particular questions or maybe questions in the free response? I've worked them all in class, but I'm willing to work them again here if I want. What kind of yeah, unhappy about this exam? No. No. Okay. Yeah. Yeah, I had rounded the pi thing. I was just estimating it. But then when I got 1200, I knew that was close to 1080. I'm sorry about that. I didn't do all that calculation. Huh? No, you did right. It's 1080 is the right answer. Any questions, Joe? I do think this is our easiest exam. But if you're not prepared, it's not going to be easy. Y'all know that, right? So be preparing. I really want to see a high grade. Y'all do too, right? Everybody does. I do too. And then after this exam, I will post some very detailed numbers about what you need on exam 4 and the final. And I'll make some estimates about your class participation. I think everybody here has the full class participation, and also the extra credit. Okay. You do get extra credit for attending today. I also posted a video, and I'll post this class as well. But I posted a video of the 3M class. We did a lot of the same questions, but they had more questions than y'all, just because they struggle more than y'all do. Y'all got our class, I think. So, is that right? Yeah, right. So anyway, they had some questions. If you want to go back and watch that, you're welcome to do it. Hold on just a second. Let me make sure as you walk out, make sure that I got your name.